Now let's start to write Lewis dot structures for molecular compounds. So the goal of this section, aside from learning how to draw Lewis dot structures, is that we're going to be able to use these Lewis dot structures in conjunction with VSEPR bonding theory, which we'll talk about later in this chapter, to say something about the shape and geometry about a molecule. But first things first, let's learn how to write Lewis dot structures for molecular compounds. You do need to memorize these rules and be able to use them. And these rules fall into three main steps, three main categories. We're going to use these rules along with the little hints I have here to write the Lewis dot structure for H3O+, also known as hydronium ion. First thing you need to do for any molecule, be it an ion or a neutral species, is to find the total number of valence electrons. And so here is where knowing the rules about Lewis dot structures for individual atoms is going to be helpful. Remembering that for any main group element, the number of valence electrons is equal to that group number. So for this case, for hydronium ion, H3+, I've got 3 hydrogens. So I need to multiply 3 by 1 for each hydrogen. Oxygen is in group 6, so I add 6 electrons. But to take care of that positive charge, or that +1 charge, I need to subtract 1 electron, since electrons are negative, to get my total valence for that molecule as 8. So in my Lewis dot structure for H3O+, I will be using 8 valence electrons. No more, no less. Step 2, write your skeletal structure. So to determine your skeletal structure, specifically what atom is going to be central and what atoms will be terminal, here is where your electronegativity table and knowledge will be helpful, because you always want to have your central atom have the lower electronegativity value. The one exception is that if it's hydrogen, you always want that terminal. You always want hydrogen at the ends of the bonds. So for this hydronium ion example, let me get my pen. Hydrogen can't be central, so our only choice is oxygen. So we have oxygen as our central atom, and we scatter our 3 hydrogen atoms around it. After determining the central atom, we scatter our remaining atoms around it. So step 2 is done. Now is step 3, distribute the electrons, specifically the valence electrons that you calculated in step 1. And so when distributing your valence electrons, it's important that you do them in the order that is listed here, which is first, make single bonds. And specifically, make single bonds from your central atom to your outer atom. And when I do that, remembering that each single bond is 2 electrons, I count by 2s. So 2, 4, 6. When making those single bonds, I have now used 6 of my 8 valence electrons. So that step is done. Next step, complete octets for all atoms. And I should say all outer atoms first. Hydrogen is the exception, because hydrogen, it doesn't want an octet, it wants a duet. Looking at our Lewis dot structure so far, we already have our hydrogens have a duet. They each have 2 electrons. So I've used 6 electrons. I've got 2 more left over. What do I do with them? If you have any electrons remain, you assign them to the central atom, which is the oxygen. So 7, 8. And that's good because, hey, now not only are my hydrogens happy with a duet, but my oxygen is happy with an octet. It has 2, 4, 6, 8 valence electrons. The only thing that's left to do, which is what you should do if you have to draw a Lewis dot structure for a charged species, is put it in brackets, and then as a superscript, put what the charge is. So those are the steps for writing Lewis dot structures for molecules and for ions. In the next video, we'll revisit those concepts and go through an example for carbon dioxide.